Today, our planet operates with remarkable stability. Predictable seasons, steady ocean currents, and a dense atmosphere all work together to support a complex web of life. But rewinding the clock 4.5 billion years reveals a stark contrast. The stable blue marble we live on originated in an environment of unimaginable cosmic violence. At that time, there was no Earth, no sun, and no planets at all. There was only a massive drifting cloud composed almost entirely of hydrogen and helium gas. Then, a massive disruption, likely the shockwave from a nearby exploding star, slammed into this cloud. The impact overwhelmed the cloud's internal pressure, forcing the gas and dust to rapidly collapse inward under its own gravity. As the vast majority of that material rushed into the center, the temperature and pressure reached extraordinary levels, until eventually the core ignited. Our sun was born. The total destruction of that quiet, drifting gas cloud provided the necessary energy and mass to ignite the gravitational engine of our solar system. Once the sun ignited, it left behind a massive, swirling disk of residual dust and gas in its orbit. In this accretion diagram, tiny particles collide at high speeds. Instead of shattering, they stick together, forming rocks. These growing rocks became planetesimals, generating enough gravitational pull to drag in surrounding material and sweep their orbital paths clear. The early solar system was a relentless demolition derby. Dozens of growing worlds constantly crossed paths, smashing into one another in fiery, high-speed impacts. Millions of years of catastrophic planetary collisions hammered these independent rocks into a single, cohesive planetary body. Because of these constant impacts, early Earth was a completely unlivable hellscape. Its surface was covered end-to-end with active volcanoes and oceans of magma. The sheer kinetic energy from the relentless bombardment of asteroids drove temperatures so high that the entire globe melted into a liquid state. This massive meltdown served a mechanical purpose. In this cross-section, gravity pulls the heaviest elements down to form the iron core. Simultaneously, lighter materials push upward to the surface, cooling to form the mantle and a solid outer crust. Without that apocalyptic melting, Earth's heavy metals would have remained scattered, lacking the vital geological shielding necessary to support a surface environment. Just as the planet began to organize its layers roughly 4.5 billion years ago, it faced the climax of its violent early history, an event scientists call the giant impact hypothesis. The young Earth crossed paths with a Mars-sized planet named Theia. They collided at thousands of miles per hour. The impact was so severe that partially remelted Earth's newly formed crust and blasted a massive ring of planetary debris out into orbit. Over time, gravity pulled that floating ring of shattered rock back together, ultimately forging the moon. This near-fatal collision gave Earth its most important stabilizing feature. The gravitational pull of the new moon anchored Earth's rotation, preventing wild climate swings and creating the exact conditions required for life to endure. With a stable rotation and a solidifying crust, Earth still faced an obvious problem. How did a molten rock acquire permanent oceans of liquid water? The answer lies in a massive dual delivery system. Water vapor was continuously released from interior volcanoes, while massive amounts of water-rich asteroids and comets simultaneously bombarded the surface from space. As the planet's crust cooled, the atmospheric vapor condensed. Rain began falling continuously for unimaginably long periods, slowly filling the low basins of the crust. Within these brand-new oceans, the chemistry of early Earth crossed a threshold, leading to the emergence of the very first microscopic organisms. These simple organisms soon developed a radical new chemical process called photosynthesis, allowing them to consume raw sunlight for energy and release oxygen as waste. Billions of these microscopic organisms spent eons filtering the atmosphere, gradually raising oxygen levels, until the air could finally sustain more complex biological systems. This oxygen surge allowed life to break out of its microscopic constraints. Over hundreds of millions of years, biological complexity scaled up, first into the oceans, then across the continents, leading through the eras of dinosaurs and mammals to the eventual rise of our own civilization. We can visualize the immense scale of this process by mapping Earth's entire 4.5 billion year history onto a single 24-hour clock face. On this scale, the entirety of human existence, every war, invention, and historical event, occurs only in the absolute final moments before midnight. And the story isn't over. The ground beneath us is still actively shifting, volcanoes are still erupting, and the planet continues to physically evolve. Our internal biology is built from the debris of these ancient collisions. The iron in our blood and the calcium in our bones originated in the hearts of distant stars, surviving billions of years of cosmic destruction to become the very elements of our bodies.